Hello, my name is Matt Gonzalez, and today I'm going to be discussing with you a paper by Gugemos and Horvath from 2005 on the comparison of environmental effects of steel and concrete framed buildings. So I want to start by looking at the learning objectives for today's presentation as well as an outline of the content. I hope that after this you're able to identify the phases of a building's life cycle and explain the impacts of each phase. I hope that you're able to identify and explain the differences in the impacts of steel and concrete in the construction phase. I hope that you're able to explain ways to improve the environmental performance of buildings, whatever the material may be. We're going to look at the introduction motivations of the paper first of all. Then we're going to move into the methods and approach of Gugemos and Horvath in the study and see some of their results and conclusions, as well as areas of potential further research. So to start with the motivations, buildings in our environment, how they interact, we have to recognize that our occupied buildings account for about 1/6 of freshwater withdrawals, 1/4 of all wood harvests, and 2/5 of energy and of industrial energy and material flows. And we need to control these impacts to stem the effects of phenomena such as climate change and preserve our environment. AEC, or architecture, engineering, construction industry, professionals have focused on this mostly through designing for energy efficiency in the occupation of a building. But this tells us that there's more opportunity for improvement in other phases of a building's existence. So one phase that we can look at that seems very environmentally intensive is construction. And what's going to make a difference in construction is the material. When it comes to commercial buildings, markets split about 50-50 between steel and concrete, with just a little bit being made up of wood, which historically is not very common in commercial buildings. And between these two materials, many factors will influence that decision. But can we factor in the environment? And that becomes the goal of this study, which is to identify environmental impacts of steel versus concrete construction over the entire life cycle of a building. As we know, one way to do this is through a life cycle assessment. And I want to preface this rundown of the methodology by reminding you that this is an older paper. It's a 2005 study. So this is when LCAs were still kind of burgeoning and before they really became a little more standardized. So the way that the authors sort of ran it down is different from what we've seen in class, but the concepts are still the same. So I've done the best to sort of tool it to match up to what we've seen so that we have a good understanding. So to start the LCA, they have their product, which is an office building, and then they have the stages, which have been reworked a bit for buildings. In the figure at left, we have our stages, starting at the left with materials extraction manufacturing combined into one stage so that building construction may be its own, because building construction is where we're going to see lots of differences we imagine between steel and concrete, followed by building use and building maintenance, which are split into their own phases as well, since maintenance activities really reflect construction activities. And then the end of life of the building is the final stage. The system boundary then becomes cradle to grave, materials to demolition, and the purpose is to aid professional decision making. As for phases 2 and 3, the life cycle inventory and life cycle impact analysis, there are two approaches that the study took, the first being a direct process-based approach used for the construction, maintenance, and end of life, and an indirect economic input-output approach, which was used for the materials extraction manufacturing phase and the use phase. So to start with the process LCA, to see what that exactly entails, this is essentially what we've seen in class. This reflects our typical modern LCA, that being where a flowchart is made of a particular process, see what the ins and outs are in inventory, and then in the LCIA, you determine quantities to relate those ins and outs to emissions and environmental impacts. And we're calling this case specific because these flowcharts and process diagrams are made specifically for whatever you're considering. In this case, it is a structural steel or a structural concrete building. And that typical process is used for the maintenance and demolition phases. But the authors of the study were very careful to distinguish the construction phase because a particular digital tool that they had developed in a previous study called a CEDST model was employed. And they wanted to call this out because they felt that this is a very detailed and very, very thorough analysis tool for the environmental impacts of a building's construction phase. And they thought that it could really make very good assessments on what's happening there. Quantities in the inventory and impact analysis were taken from RSMeans, which is a industry standard publication for cost estimation, and from federal publications on emissions regulations for construction equipment. The second LCA method they use is the economic input-output LCA, or EIO, and this is being called an indirect approach because it's based on national averages of industry processes. So not for specifically, this is a steel building we're looking at, but what is the steel industry doing, and how do we relate financial figures to emissions and environmental impacts? So what this means is that the authors had to determine quantities, cost quantities, and then put those into a model to get out their impacts. The quantities were estimated again from the RSMeans industry publication, and the base economic year for these considerations was taken as 1997. And on the left, we have just some of the figures that they found for this, being the cost of certain materials for each building. For example, in the steel frame building, we can see that there's about $100,000 of concrete used. They could put that into their model to see, okay, what is the materials extraction impact for that financial amount of concrete? To apply this LCA method, or both of these LCA methods, they developed a model fictional building that is identical in every way, except there are two versions, one with a steel structure and one with a concrete structure, assumed to be in the Midwest United States. The material quantities were determined for each of these. What they found is that the steel was more expensive, but the concrete weighed more, and that'll be important in a little bit. They assumed in this building that 25% of steel was recycled, and 10% of the concrete aggregate was recycled crushed concrete. They assumed that the building would have a 50-year life, followed by demolition to ground, and that the use and maintenance phases were identical, with the electricity of the use phase being 184 kilowatt hours per year per meter square floor area, and the gas usage being 17.5 meter cubes of gas per year per meter square of floor area. They did not include waste processing in their analysis because the amount of the waste that could be potentially recycled would really depend on year-to-year market conditions. If it's very cheap and viable to recycle steel in 1 year, then lots of that material is going to be recycled and would have environmental impacts related to that process. But if it's not lucrative to recycle in another year, then not much would be, and then there's a different set of impacts from landfilling. So to eliminate that variability, they did not include it in their analysis. So as for the results of this LCA, they started by looking solely at the construction phase before the full life cycle, with the reasoning being that this is where AEC professionals will have the most impact through their design. What they found is that the concrete was, on the whole, more impactful than steel to the environment. They found that it used about produced about 2 times more carbon monoxide, NO2, carbon dioxide, particulate matter, and SO2, and it used about 2 times more energy. The reason for this is because remember how we saw that the concrete was a much heavier structure. Those large volumes and masses of material were very intensive to transport. There's also lots of temporary materials that get thrown away in a concrete structure, namely formwork, and there's a longer duration of the construction phase. As for the steel, they found that it produced 2 times more heavy metals and 3 times more VOCs, and this is due to the cutting, welding, and painting operations that come with structural steel. So moving on to the full life cycle from just looking at that construction viewpoint, the differences became marginal, unfortunately. And the reason is because the use phase was assumed identical, remember, for each building, because they didn't think, well, steel and concrete, that won't really affect how much electricity people use. But the use phase accounts for 80% of life cycle energy and 60 to 80% of full life cycle emissions, depending on emission category. So this identical factor dwarfed all the differences pretty much. So to try to take a little bit more detailed look, see where other differences might be, they also looked at the full life cycle without the identical phases, without use and maintenance phases. So this is just materials, extraction, manufacturing, construction, and demolition. In this case, the differences were still small due to the impacts of steel and concrete manufacturing kind of canceling each other out. And this is visible in the figure left, for those 3 life cycle stages, what the environmental impacts were for each structure. And there were some marginal differences, being that the steel used more or produced more SO2 and carbon monoxide, and the concrete just a little bit more NO2. But on the whole, as you can see, pretty similar between the two materials, and hard to say if one could be better. So to do their due diligence, the authors of the study also compared their findings to existing research at the time. The first study they looked at was by Cole in 1999 on steel and concrete construction impacts from just the construction phase, which was a big focus of the present study. The Cole paper exceeded the conditions of the present study by including worker transport and climate control on site. But the Guggemos and Horvath study we're looking at still showed nearly 100 times more energy being used in the construction phase. And the reason is because the Cole study did not include heavy equipment like cranes, dump trucks, and so on. And so the Cole study was determined to not really be a valid reference point to compare to, because that's a pretty large discrepancy in the assumptions. They also looked at a study by Bjorklund and others from 1996 that considered embodied energy and emissions of buildings, where embodied energy and emissions basically means energy and emissions of materials extraction, manufacturing, and construction. So the present study once again exceeded the values of this study, with this being chalked up to differences between US and Sweden construction practices. But one similarity that validated this study was that the concrete was again seen to be, for the most part, more impactful in the construction phase. Some further discussions and conclusions from the authors is that the use stage energy efficient design strategies are well targeted. So things like LEED, those are steps in the right direction, because that's where, as we saw, 80% of building energy is being used. So making energy efficient buildings is a good approach. Some opportunities for improvement on building environmental performance are to limit and reuse temporary materials, try to use more efficient equipment for construction processes, so dump trucks, heavy equipment, use the most modern and most regulated models. And then, of course, recycling, so recycle as much material as possible. One additional thing that they called out that they didn't expand on much because it wasn't super relevant to the scope, but was still worthy of discussing, is that they observed problematic quantities of solid waste being produced. And they posited that the best way to prevent this is through more shop work, especially precasting with concrete structures. Some further research opportunities that I personally thought would be interesting to see were to maybe see if the use maintenance phase being taken as identical, maybe there's a different way to go about that. I think that one thing that could be included is that the phenomenon of steel thermal bridges in steel buildings, where when you have steel structure penetrating the insulation layer, it basically forms a path for cold or hot to get in and drive up the gas bill pretty much. And that's an illustration in the left there, where you see the sort of the thermal spread of a steel structure from inside and outside. And there are also some differences in maintenance that you could expect between steel and concrete. Another thing that I think would be good to look at is incorporate wood as an option and compare that to steel and concrete. The reason being that even though wood isn't really used in commercial buildings at the moment, burgeoning technologies such as cross-laminated timber construction is making very large wood structures viable, up to like 15 to 20 to even 30 floors in the United States. And it would be nice to see how employing this wood option could make some environmental impact improvements in building construction. And that is all I have. This is the citation for the paper, and I hope that you learned something and that you get an A on the quiz.